In this video I want to do a pretty quick example of reverse compound curves just so we can solidify the two equations we derived in the last couple videos. The first being P, which is the distance from a parallel road or a perpendicular distance from a parallel road to another parallel road, right? The distance between them. And the second, which is L, or the transition length, which is the length it takes for a reverse compound curve to transition between a straight segment here and another straight segment here. Okay, so we have two different curves, each with their own different radii or radius. This would have a radius 1, this would have a radius 2, and if you remember from the last video, this would be delta, this would be delta, right there. Opposite interior angles, so they're the same value. The problem says that there are two reverse horizontal compound curves, and curve 1 has a degree of curvature of 8 degrees, and the second curve has a degree of curvature of 10 degrees. And this curve is used to transition between this road and this road down here. The roads are 900 feet apart, and the question wants us to figure out what the central angle delta is and what the transition length is, the distance, this distance right here. So the first thing we want to do is figure out what each of the radius or radii are for these two curves. Since we're using a degree of curvature, and we didn't say this is a railroad, we can assume a freeway definition or an arc definition of degree of curvature. And if you remember from several videos before, we have this formula. We have 2 pi r over 100 feet is equal to 360 degrees over the degree of curvature. And remember, degree of curvature is a specific interior angle that corresponds to an arc length of 100 feet, always. So for curve 1, if we plugged in d1, or the degree of curvature for curve 1 is equal to 8 degrees, we'll get something like this. 8 degrees, right? And if we punch this into our calculator, we'll get R1 is equal to 716.20 feet. And similarly, we can do this for curve 2. 100 feet is equal to 360 degrees over the degree of curvature for arc 2, or curve 2, and that's 10 degrees. We plug that in, we get R2 is equal to 572.996 feet. Okay, so we figured out what the two radii are. We can use this information to figure out what the distance P, or I'm sorry, the interior angle, what the value of the interior angle is, and what the transition length L is. Okay, so let's do that. Since we have radius 1 and radius 2, let's use the first equation to come up with our interior angle. So down here, let me do that in orange. P, which is 900, is equal to R1 plus R2, and R1 is 716.20 plus 572. This is radius 2, right? 0.96 feet times 1 minus cosine delta. So if we do the math for this equation, I'm not going to do it. Well, I already did it, right? So delta would turn out to be 72.43 degrees, and if we convert that into degrees, minutes, seconds, we'll get 72 degrees, 25 minutes, 48 48.5 seconds. Okay, so delta, or the interior angle for both of these curves, is 72 degrees, 25 minutes, 48.5 seconds. So we actually figured out what delta is. Awesome. So the next thing we need to figure out is what the transition length is, what the transition length L is. Well, L is just the sum of the two radii times the sine of the interior angle for both of these curves, or sine delta. So the sum, let me do that in purple. Purple's a nice color, right? We have this formula up here, R1 plus R2, the sum of the two radii plus, or times sine of delta. So the transition length is equal to R1 plus R2, 716.20 plus 572.96 times sine theta, right? Or sine delta, delta. Sine delta, sine of this thing right here, 72, 25, 48.5, right? And if we plug this into our calculator, we should get L is equal to 1,229.02 feet. Okay, so we used what we knew about reverse compound curves to figure out what the interior angle for both of these curves are, and we figured out what the transition length is. And those answers are right here. Alright?